The D command says I want to take a difference. So it's going to give me the, in this case I can specify the difference. So if I say D1, it's going to give me a first difference. If I say D2, it's going to give me a second difference. If I say D3, it's going to be a third difference, and so on. So a fast way of sort of creating differences in Stata is just to use this command right here. So it's just D1 dot and then the name of the variable that you want to
Is
difference.
that the D that's on the board right there?
Exactly, yeah, okay. And or, if I want to have a lag, then L stands for lag in Stata. So I just put a capital L and then L1, and that's going to give me unemployment lag one time period.
Okay, so we don't need to like generate another variable, it just...
No, it just
it's
does it
already
for
there.
you, exactly. I'm integrating the variable, but I'm just making it an easier step. Instead of having to type out the whole equation,
Yeah.
Stata says, if it's working with time series, it's either going to be a difference, it's going to be a lead, or it's going to be a lag.
Okay.
So it kind of gives you those three choices. So the F is going to be, F means forward, and forward just means a lead, that's all it says.
Gotcha.
You can't use the L because you already use it for lag.
Yeah.
So use F for forward.
Okay.
Okay.
Cool.
So it's just a really, really fast way instead of being able to create leads and lags and differences. Okay. Just saves typing, that's what it does, okay? To convince ourselves of that, we're also going to list it out just so you guys can see the difference. Right? So you can actually see it actually works in this case, right?
Did you say the F was for the...
F is for
Lead.
for a lead, yeah. So F just means forward. Okay. So all that said then, so again, we'll just go ahead and run a couple of these. We know the first one's going to just open up the data set. The second one's going to open up the log file. So let's go ahead and just get those started. So we'll run those. Again, there's our results window. So again, it tells me if everything is in black. Again, it tells me everything seems to be working here. So the next command that I have in the do file, though, is to go back and to just browse the data. Again, I have it just in the do file just to remind me that I want to make sure I examine the data set. So again, when you highlight things in Stata and then just click on run over here, it'll run just the part you've highlighted. So there's my data set. Okay. So when you go back and look at this, then again it has these two windows over here. Right? So it has the variables over here, so it tells you what variables in the data set. And also, it's always a good idea to label things so you don't forget what they are. Okay. Over here. And it also tells me when it sort of is highlighting a variable in this case, so like for example date or unemployment. If you look down here in properties, it then tells me what the name is, it tells you what the label is, and also tells me what type of variable it is. So for example, again, like if I'm using a data set that has countries that might be in a string, it'll tell me right there it's a string variable. So if I see it, if I forget the color, if I look at it here, it'll say string. So I know I have to go back and convert it from string into numeric. Okay. So in this case, just to show you real quickly, so we just examine kind of this data set. So it's just a time series, okay, of unemployment, the consumer price index, the federal funds rate, and then also the growth rate in GDP. The key part I want you to look at here is the date. Okay, so in this case we have this date, and it appears to be in a format that's quarterly, right? So I have 1961 colon 04, and it goes to 62 colon 01, 62 colon 02, 03, 04. So it appears to be quarterly data. Okay, so that is good. As I go down through here, so it all looks like it's a pretty complete data set. Keep examining just to take a look at it. And then all of a sudden I get to observation 173, and I have this much more odd looking indicator of time, right? So now it says, yeah, I'm still working now in terms of a time and date variable here. But now it's the year 2000, it's a quarter here, but now it's sort of thinking there's going to be some sort of indicator of month over here. Right? So it's a different data format. So they're just going to go back and say, I don't know what to do with this, or different formats, you know, so give me this, the same or consistent format. So in that case, I go back and say, well, I'm going to have to convert this thing. So I close out of the browse. I go back and say, well, I've got to clean this data set. And so let's clean it now by sort of generating now a new variable called date1. And I'm just specifying that I want to have a subcommand here. So I want to sort of begin to, in some sense, take this date that I have. I want to convert it to a format, date being the 1 here is going to be the quarter, and then annual, and then the 7 just means a quarter, right? So it's just a command within Stata just to tell me to convert this now to an easier to look at data set. Okay? So we're going to clean that first. Let's go ahead and run that. So I do. Now I go back and I look at this, and I go back and say, well, just show me these two to see if I've actually done a good job of converting those. Okay. So it was back and around for that variable 171. So again, it seems like I've been able to convert maybe some of this, but not all of it. So it's not enough. Back to our new file here. Close out my new file. So now I want to convert. If I have sort of string variables here, I want to convert those now to being numeric. And so that's going to be this command here. So again, I list it, so take a look at this. So now I have date 1, and now I'm going to create this variable called date var, and I want to sort of convert this so I remember that these are actually going to be quarterly data. Right? So I have the numbers in here, but I want to be able to think about them as being quarter 1, quarter 2, quarter 3, quarter 4, and so Stata allows you to be able to do that and still recognizes this as being a numeric variable. So that way I know that this, so also when somebody else reads this or looks at this, they'll go back and say, well, what does 57:1 mean? 57:2 mean? 57:3 and so on. So I just got to convert that just to make it a little bit easier to be able to read. Again, we're down to sort of the last ones down here. So remember that these were sort of confusing here. Converted them over to be essentially now in the same format, right, as the date variables from before. And now I converted those to be a year and then a Q1, Q2, Q3, Q4, just to make it easier for me to be able to recognize what it is. Make sense? Okay. So that's all I've done with that conversion there. I want to go back, and because I've converted this and I kind of like the way it looks, I'm going to go ahead and back and save it again just so I have it. Okay. So I've already done that, so I'm not going to go to save it again for you. I want to tell Stata that this is now a time series data set to be able to work with. I want to do it off of the date variable. So I run that command. Again, Stata says, yes, that sounds fine. So now it knows it's going to be a time variable. It's going to use date variable as its time component. It's going to go from 57, quarter 1 to 2005, quarter 1. And the delta is going to be 1 quarter, right? That's my change in time. So I know that's exactly what I want to work with now with my data set. I want to generate these differences. And I want to list them out so I can see if I actually converted them or not. So we'll do those and then just list them. And again, the listing in 1 through 10 just says, look at just the first 10 observations of this. I've looked at the whole data set, just the first 10 to convince myself.
So with these different options, you're trying to figure out which is the best transformation? Or you want to do those different ones?
Exactly, yeah. So I think I'm going to probably have to, because of the way that the box sequence kind of suggests we kind of work with this, I know that I'm likely going to have some sort of ARMA component, some sort of moving average component, perhaps, or some sort of integrated component also. So I've got to worry about what these leads, lags, differences might happen to be, and also what a moving average might happen to be. So I'm just kind of setting them up and saying, I think I'm going to have to solve for these. Let's just pick a couple of these and just generate the variables, so I might have to use them kind of later on. Just have them already there. That's all I'm doing. Does that make sense?
Mm-hmm.
Yeah. So I'll run those and go back and look at them. And so you'll see right away that my unemployment L1 here is just unemployment, but now lag 1 time period. In my unemployment L2 here, this is just my unemployment variable, but now lag 2 time periods. My difference is there, right? So it's just that minus that. And if I difference it twice, then go on and so on and so on. So it's just a really fast way of working with time series and data, because you know you're going to have to use leads and lags and differences. It's a very fast way of just generating variables to work with. Okay. So now I want to go back and begin to examine the time series itself. And so I'm going to focus here upon unemployment to see if I can actually begin to predict unemployment and forecast it, and then see how I might happen to forecast. And so here, the ways of doing this in time series is you graph this thing called the parallelogram. And you can specify the number of lags. I just picked a number of lags equal to 12, so it's going to be, this is quarterly data, going to go out for 4 years as a lag in effect. I think that's going to be long enough to sort of be able to determine some sort of effective unemployment. You can specify the lag length of whatever you want initially. run that, and there's my result, okay? And so I'm going to be able to start to use these functions here, the autocorrelation function here, and the partial autocorrelation function here, to tell me something about both the moving average component parts and also the autoregressive parts of the equation. Right, so you'll be looking for my P's and my Q's here is what I'm looking for. Okay. So the idea is that we can test for this, and essentially what these are, there's sort of giving you, in some sense, values of the autocorrelation function here, the partial autocorrelation function here. This is a Box-Yang test for significance here, the probability that you in fact have a stationary series or you don't. And so the autocorrelation part here is going to tell me something about the moving average component part. It appears to me it actually has, in terms of a moving average, this seems to be a relatively smooth sort of process where it's moving down towards zero as we increase our lag length. So by looking at this, because I don't have any spikes over on this side over here, just by looking at this picture itself, it gets me that I probably don't have to worry about a moving average part of my equation here. So I'm not going to worry about a Q part of this equation at all. Doesn't really have to be there. Okay?
Can you explain that one more time? Why, how you know that?
So what I'm looking for here is these spikes, right? So I want to see whether or not I actually have a smooth sort of transition down towards zero as the lag length increases, is what I'm looking for. Just as a picture, okay? And if I begin to see either spikes in this, so it starts to jump from one side to the other, or if this doesn't have sort of a smooth transition down like this, whenever I see the spike in there, the spike is going to indicate to me in some sense the moving average component part. Okay?
That you need one.
That I need one, exactly. Okay. Over here in the partial autocorrelation function, I'm also looking for spikes as well. Okay. And so here it should be a relatively sort of smooth transition that goes kind of back and forth that eventually ends up here very close to zero again. But because I have a spike sort of right here, it appears to be a relatively big spike, and also a spike here, indicating to me that I'm probably going to have some sort of autocorrelation problem in this model, so I might want to go back and correct for that either by using an AR1 model here or an AR2 model here. Okay. I could also go down here and say, well, I could use an AR10 or an AR11 or AR12 model, which make a lot of sense because by then most of the autoregressive component is going to be already lost or eaten up. So I'm going to focus in upon testing now in my model for forecasting. I'm going to probably forecast then either an AR1 model or an AR2 model. What it tells me. Okay. I can see that more exactly by actually doing a graph or a plot of the autocorrelation function here or the partial autocorrelation function here. So that's my next command.
So what's that negative partial autocorrelation tell you? Like how's that?
Yeah. So just to help you with that, let's flip back to here to help you guys. So flip back to page 14
In which one?
on the time series, right? So we're doing time series. And so these are the commands we had just run, right?
Yeah.
Okay? So we have the parallelogram, which is the first one. So that's just the picture that we just saw, right? So we have, let's pull that picture back up. So our picture looks just like this, right? So what it tells you is, again, you know, we're looking at the AC part here, right? So it's telling you sort of the current value. It compares it back 3/4, right, is what it's doing. So it goes back a certain time period, and it's going to tell you, in some sense, what that moving average component part is going to be. So we're looking at sort of this sort of value over here, okay? Again, the PAC part is indicating to us this idea about the autoregressive part, okay? And then, again, the Q test is just this box here. It's also called the Box-Yang test. And then the probability, and then just the graphical view. So again, it's just a way to remind you of kind of what those things are telling you. Okay. We're going to extend that though, and he actually doesn't do this. This is where he kind of stops. He kind of jumps right away into a vector autoregressive model. We're not going to do that. Okay, we're going to kind of stop with this and kind of extend on. We're doing just a simple, in this case, again, univariate time series model. Okay, so the parts beyond that begin to relate back to VARs and to ECMs. Okay. But for us, let's go back and examine these functions more carefully, okay? So we can begin to understand why you might use this AR1 or AR2 model to forecast. So now if I want to go back and look at these, again, I'm trying to look at these to determine the value, right? The ACF and the PACF to determine the P value for the AR and or the Q value for the moving average. There they are, okay? So nice part is these kind of give you the bounds kind of around here, and again you can start to look for these spikes, right? So the spikes are going to indicate things that are sort of outside of what we think is the probability that we have a stationary or non-stationary sort of time series here. And so again, this is the PAC, so this is again telling me sort of the autoregressive part. So again, I have a spike that's outside of my bounds here, and a spike that's sort of outside of my bounds here, right? So again, it tells me, in terms of my autoregressive component part, the P part of my equation here, it's either going to be an AR1 or an AR2 model that I want to sort of specify. Okay, so I'm looking for the number of spikes that are sort of outside of this bound that happens to be here. Again, there's sort of these two spikes out here, but again, they're relatively small in terms of being outside the bounds. And again, by then, most of the autoregressive component is going to essentially deteriorate as the number of lags increases. So I'm more worried about sort of the 1 and 2 lags over here. Okay. This is again the moving average component part here. So again, with these sort of 95% confidence intervals. And again, I'm looking for this to be sort of this smooth kind of line that kind of goes down like this. That tells me that as the lag length increases, that this moving average part really isn't going to improve my model very much at all. Because it seems like it's moving down towards 0 here anyway, as I extend the lag length down. So it's telling me that a moving average part doesn't exist in this model, I think, is what it says. Okay. So for specification, I'm going to try an AR1 and an AR2 for forecasting, is what it says. All right? Does that kind of make sense?
So why do they have that kind of parabolic symbol? Like, what does that tell us?
It's just it's kind of the bounds of the Q test is all it is what it says. Okay. So again, you're looking for sort of these spikes that kind of go up and down like this. So if you see spikes that are kind of going up and down like this, it indicates to you that you're sort of, that the moving average would then be an important part to include there, because it says that the data, in effect, may be influenced by an average value 1, 2, or 3 periods maybe ahead or behind either way. Okay?
So we know that lagging a whole bunch of periods now based on those last two graphs is not the way to go.
It's not going to help you very much, is what it says. So typically, in terms of the p values or the q values, and even the difference values, we typically aren't going to go out much more than sort of a 2 or 3 or even a 4 time periods in practice, because for the most part, once you sort of get out in terms of lag length, you move beyond that. In effect, most of whatever you're trying to capture is going to be already captured in the data before that. That's what happens. So by trying to lag it out to time period 20 or 30, whatever it has to be, it's not going to help very much in terms of forecasting. Does that kind of make sense? Okay, so just to sort of get around the time here pretty fast. Just going to move on a little bit. Again, these are just comparisons of the information criteria tests, and I can do some unit root tests here as well. And I can do the unit test in terms of Dickey-Fuller tests and also these Perron tests. And again, as you read through this, I'm going to just tell you how to be able to test for the unit root or for stationary in your time series, right? Because if you don't have stationary in your time series, then in effect the time series blows up. So it instead of collapsing down to a unit root, it will expand, and then you won't be able to forecast very well, is what it says. Okay, so I'm not going to go through this because we have to be done in like 5 minutes, okay, I guess. So I'll jump ahead here.
Does this go through if you did need a moving average, how you would do that? Is this?
Unfortunately, it doesn't. So if you guys want, what I can do is I'll add on to this. If you want, I'll add on how to determine if you have a moving average or not. Would that help you guys?
That'd be great.
Okay.
So basically, if that happens, then you're just you'll just somehow tell your model that you're going to include that in there?
Exactly. Because what you're doing is you're really looking for this whole ARIMA part that Hyder's talked about up here. You really have to figure out what's going to be the P part, right? Because the P goes with the autoregressive part. The Q part goes with the moving average, and the D goes with the integrated part. You have to test for all these things to determine which one is which, right? So which one is going to give you the best fit for the data that you happen to be working with.
Okay. So it's not necessarily bad if you have one.
No.
It's just do you have one?
Yeah, exactly. And so
Okay.
the idea is that you want to try to find the best model that's going to fit your data the best, because you're looking at the data to tell you what the best model is going to be in this particular case. So you're looking at past values to sort of use it for forecasting purposes. So the idea is that you want to try to specify the model in the best possible way. So we're doing all these tests here to come back and say, well, what's going to be the appropriate value of P? What's going to be the appropriate value of Q? What's going to be the appropriate value of R? Okay. So do I need to difference this model, or do I not need to difference the model? I'm going to have tests to kind of help me determine it in some sense. Do I want to include this moving average part or do I not? Well, in this sort of example, the one that I have here, the moving average wouldn't really help us in terms of forecast. It might actually make the forecast worse in some sense. Okay. And I think you're going to see here at the end that with this sort of autoregressive model, I think it's an AR2 that I'm going to use here, it actually forecasts pretty well, which I'm going to show you a picture of in just a second. But the whole idea is to try to be able to get the best fit before you forecast. And that's why you spend all this time sort of examining the data, testing it, and then find the right model, and then use it for forecasting purposes. That's what we do.
Would you use this for any other reason except to forecast?
Generally, no. I mean,
Okay.
these time series models are almost all for forecasting purposes. So whether it be forecasting an individual variable, in this case like unemployment, or beginning to extend it, which is sort of what Heidi's going to sort of do for you guys next, the VAR model is going to be an extension of this sort of simple time series model. It's going to be a time series model technique, but essentially using multiple variables. So it's going to be including something like unemployment and GDP, okay, or
To
unemployment
predict
and
both of
interest rate.
those.
To predict both of those, exactly. And you have to test then to go back and see if there's a co-integration between the two of them. Because if there's a co-integration between the two of them, they're moving together, then one variable's values may impact upon the forecast of the other variable's values. And if you don't correct for that, you're going to forecast this variable incorrectly because it's picking up all the influence of this one over here. So you want to separate out the effects before you forecast one or the other. That's what you want to do.
So could you also use that for like a policy prescription?
Exactly, yeah. Yeah, and so as it turns out, for forecasting purposes, most people now are using time series methods to forecast the economic variables. So whenever you see forecasting models that people say, well, GDP is going to be 3.4% higher next year, they're using models just like this to kind of make those predictions. So it's almost all time series forecasting. And so the stuff he was talking about with Robert Lucas, he came back and he said back in the 1970s that these large-scale macro models are subject to policy regime changes. And so because of that, they tend to forecast poorly. So as a result of that, all this work in time series began in the 1980s for the most part, and it started to develop then forecasting techniques that just looks at the data itself to try to be able to improve the forecast of the economic variables. The last set of models you're going to talk about is going to be these error correction models, which they do make reference to kind of in here as well. And I can send you guys, if that would help, also another link to sort of what the error correction model should look like, because they get a little bit more complex. The testing gets a bit more complex, but they sort of take the idea that in sort of time series models, they can also have, because they have sort of this moving average component that goes with them, they also can have heteroscedasticity that exists, right? So their variance can be non-constant, and that's going to affect then the value of your, the predicted quality of your forecast. So the error correction models begin to take those things into account overall. So they try to collect for autocorrelation and for heteroscedasticity at the same time. And those become what are called Garch models. So they're generalized autoregressive conditional heteroscedastic time series forecasting models is what it becomes. Right? But again, there are different techniques as the key part. So all this said, let me go ahead and we'll just run the test here.
This is why I reiterate you should have the time series classes.
Yeah, and I'd love to do a time series class because this stuff is really, really interesting. And you'll see it's completely different than the stuff we did from before, right? Completely different. But it's really, really powerful stuff to know how to be able to do. So here's just a time series of the data itself, right? So we're just looking at the data. So this is the unemployment rate overall. So this is the actual data, okay? And then I'll show you back here. So here are all just the different tests that we've run, which this explains a bit, and also explain it when I send you guys some detail about this as well. But I want to jump to the forecast so you can see this. So I'm actually going to run 3 different models. I'm going to run here, and these are ARIMA models. So the command in Stata is ARIMA, right? And that's going to, it'll take account of whether it be just an AR model, whether it be an AR-MA model, whether it be an MA model, or whether it be an AR-IMA model. It will recognize any of those depending upon what you specify. So I'm specifying that I'm going to do an ARIMA model of unemployment. I'm going to specify it just being an autoregressive model of order 1, so P is equal to 1 in this case. We do the same thing with an AR model equal to 2. Those are the 2 spikes that I saw in my partial autocorrelation functions. I want to test for both of those. And then I thought, well, maybe I should do a first difference. I'm going to include a difference in there as well and see what happens if I do a first difference, and I also run the autoregressive model on that first difference and see if I can improve my forecast by those 3. So let's go ahead and run those. Then I'm going to run an ESTAT command, which is just going to be our, remember our IC command, which is just our either our SIC or our AIC, the Schwartz Information Criteria Test or the Yankee Information Criteria Test. Again, all I'm looking for there is the value that happens to be the smallest. And so the one that has the smallest either SIC